Hello, and this is going to be homework 1, part B. So in homework 1, part B, we are going to derive the time-dependent material and energy balances, the energy balance equations for the CSTR described. We are then going to code, solve, and plot the time-dependent concentration and temperature profiles for the CSTR when the coolant temperature is 305 Kelvin at time equals 0. So what I'm going to be doing is I am going to get on the board behind me and derive our material and energy balance equations before I end up coding it out in Colab, and then we will be able to see how the temperature profile and concentration profile change when we set our when we set our coolant temperature to 305 Kelvin at time equals 0. Hello. After reading the problem, I went out and wrote a few things out about this problem, but we're going to go through most of it together on the board. So what you see here is kind of an example of what this problem looks like. So we have an overflow reactor, meaning the volume is fixed for this type of problem. As things go in, things come out, but overall, there's nowhere for material to go besides in or out. We also know that as a cooling jacket, which is what this outside looks right here. So in is, we're going to say this is the temperature of the cooling jacket and then the temperature of the cooling jacket. One thing about this problem we're also assuming is that this flow rate is so high that it's not heating the cooling jacket. So it's the temperature of this jacket is uniform throughout. So we know that the volume, and we know the temperature. And the other things we need to talk about is the reaction. And this reaction is a simple A to B reaction, in which the rate is defined as K times Ca equals the reaction rate. We also know that because of this cooling jacket, the reaction is exothermic. So now we need to create our mass balance. Another thing, we can kind of assume or figure out by looking at this is that because what comes in, what comes out, we can say that Q in, or the rate of material coming in, equals Q out. So let's start writing our material balance. So we have dV times Ca over T, or dt, equals we're going to want the material coming in minus the material coming out minus the material reacted. So we're going to say this is just generic Q, because Q in equals Q out, we can just call it Q. Q times Ca, because we have material Ca that's coming in, and then we have just the material, or Ca in, minus the material, which we're going to call Ca at the out. And we're doing this because this is a continuously stirred reactor. So once the material gets into this reactor, it's uniformly stirred. So we can just call this Ca in as the material coming in minus Ca, or Ca out. So we have in minus out. Now we also need to subtract the amount of material that's being consumed in this reaction. So lit, which is going to be Kc, or just K, times Ca, as we have the material in, out, and consumed. But because the volume is constant, like I said earlier, we can actually take this out of the formula. So we can take the volume out and then divide it across. So we end up getting our material balance of dCA over dt, or the change in concentration of the tank over time, equals Q over V times Ca in minus Ca, subtracting by K times Ca. And one other thing is that Q over V is also known by another name called residence time. Sorry, I'm stepping on my charger right now. I'm pulling it out of the socket. And I believe this is actually our material balance for this, because we have exactly what's coming in, we have what's coming in, minus what's coming out, minus what's being reacted, because we have the concentration of A, and the concentration of A is also being consumed by the reaction. So next, what we need to do is an energy balance, which are getting ahead of myself, but our energy balance has a few different parts. We have the temperature of the material coming in minus the temperature of the material coming out, subtracting by, again, the amount of material, or what's being cooled. Excuse me. There's also the reaction. We have our cooling jacket, we have the material coming in, and our reaction, which is heating the material coming out. Those are the three parts of our energy balance, which is what I'm going to do next. I'm going to keep a few things on the board. Let me just circle this so we have definitive proof. I'm going to erase our material balance. Just let it be known that our material balance is dCA over dt, or change in concentration over time, equals Q, or our rate of material, divided by V, our volume of the tank, multiplied by the concentration coming into the tank minus the concentration coming out, subtracting by the reaction rate, or how much A is being consumed. So K times Ca. And I'm going to erase this, and then we can do our energy balance next. So now it's time for the energy balance portion. So I wrote down a few more things that we know and just let down the units because I was having a hard time remembering. So for example, we have the specific temperature, specific heat, which is joules per kilogram Kelvin. We also have U of our cooling jacket, which is joules per second Kelvin meter squared. And because our reaction is exothermic, means we have a negative HR. Because that value is already negative, that in turn allows it to be a positive value in the aspects of this problem. So first, we're going to do D. For this, we're going to do the in minus out, and then we got a few other things you got to add. So D, we're going to do big parentheses. So we C, which is in joules per kilogram Kelvin. So if we want to cancel kilogram, we need to multiply by the density and the volume. And because it's in Kelvin, we multiply the temperature. And this ends up giving us joules per second. You can't read that. I'm going to enunciate. Let's just see. There's a little bit of a glare. I'm going to enunciate because I know it can be hard to receive with the glare. So now we're going to be doing in minus out. So for in minus out, we need to know Q. So Q is most definitely going to be in there. And I forgot dt, of course. So now we want joules per second, because this is joules, I want joules per second. So Q, which is in terms of, liters per second, I believe, or moles per second, my bad, multiplied by C, which is in terms of joules per kilogram Kelvin, times rho, because this is in terms, this is kilograms per meter cubed, or liter, my bad, I keep mixing up which units. That will end up canceling here, and then this ends up canceling. So then we just multiply by temperature, and we end up getting our joules per second. So our temperature is going to be what changes. This is our in minus out. So our in is we're going to have our temperature knot, or our T, depending on how you wanted to designate that. And then when we're going to subtract, our out is the temperature of the tank. So our temperature of the tank, because it's the same as what's coming out of the tank, because it's, again, evenly stirred in a CSTR, or evenly mixed, minus T out. The next thing that's going to be added, or the next thing that's going to add heat to this problem, is going to be the reaction, because it's exothermic. So because of that, we're going to do a plus, and now we're going to do negative HR, which is in terms of, let's see, joules per mole, right? Yes, joules per mole. And then we're going to multiply by Ca, or the concentration in the tank, times Ca, which is then in terms of mole, but we need this in seconds. So now we're going to multiply by K, I believe. I also believe I'm missing something. Then we're going to multiply by K, because K is in terms of 1 over second. Oh, yeah, by K, which is the K from the reaction rate. I do believe I'm missing something, but we will keep going, and I will come back to this, because I don't believe this is working out. This works out correctly. So what's going to subtract or take away heat is our cooling jacket. So our cooling jacket is all defined by U, which is in terms of heat transfer, kind of our geometrical fudge factor, essentially. So U is joules per seconds Kelvin meter cubed. So we're going to do minus U, so make sure you can still see, which is, like I said, joules per second meter Kelvin. We want joules per second, so I'm going to multiply by the area. And what this area is all of the surface area in which this cooling jacket is touching the tank. So basically every opportunity it has to draw heat from the tank. And then we're also going to multiply by joule per second Kelvin. So this is going to be our T minus TC, as our driving factor for this. Sorry, you couldn't see me right there. Times T minus TC, because this ends up giving us our joules per second that we require. So our next step once we figure out, let me see if this is wrong, is we're going to pull out a few different things because they're constants. So let's see, out of our derivative, what's a constant? We know that our specific heat, so our C is a constant, so we're going to pull that out. We know that our density is a constant. And we also know that our volume is a constant because when our material balance, we explained that because it's an overflow reactor, that volume is going to stay consistently the same. So it leaves us with CPV dt over dt. And now we're going to divide across by CPV. Yes, now we're going to divide across by CPV. Let me just double check my units. And I will do this right away once I double check that these units are correct on the reaction term, because I'm getting heebie-jeebie vibes from them. So I ended up finding what I messed up and why these units were throwing me off. It's because Ca is, of course, in terms of moles per liter. And it just blew my mind that I forgot that, which ends up, let me just erase this subtraction sign, which ends up giving us, we need another something to cancel out liters, so we're going to multiply by volume. And then this term was correct. Okay? So now, as I said earlier, are going to divide across this entire equation by CPV. So what this ends up giving us is we are going to equal dt over dt, which is just a great unit, equals, let's see, we have C in rho. When I've been saying P, I mean rho. We have C in rho, that cancels out, so we're going to have Q over V. Wow, that's kind of ironic that it also happened in our material balance. Times T minus T out, or T tank, depending however we're going to determine it. Plus, so we have HR, CA, K, and V. So we have V, which is going to cancel, so it's going to be C times rho over under this. We have negative HR times CA times K over, what was it? We're going to cancel over C times rho. Now we're going to subtract, as there's nothing on this term that specifically cancels out. Well, units it might cancel out, but in just full-on terms it doesn't. So we're going to just U times A times T minus TC all over CPV, or C times rho times V. And this actually ends up being our energy balance equation, as we have our change in temperature over our change in time equals our in and out. So with the material coming in, the material coming out, the flow of that material is temperature, plus what's heating up the material, the reaction inside the tank, causing the change in temperature here, minus, this is an ugly looking U, kind of looks like a V at this point, minus our cooling jacket, which is U times A times temperature of the reactor, T minus TC, which this is also the same here, because this is T in. So we're going to call this T out, just because it might cause some issues if we don't want them to designate them being the same. So minus T out minus TC all over CPV, or divided by CP in the term for the second term. So now what I'm going to be doing is I'm going to be coding out this in Google Colab. I'm going to write down all of the givens beforehand, just because, as you can see here, we know a lot of these terms. We know this term, we know this term, we know this term, we know these terms. And that's going to be a lot of just me copying and pasting. So I'm going to write that down first in the Colab, and then we're going to derive our then we're going to plug in our derived equations into our differential equation solver, or into our function, which then we can then solve for, as we have dt in our energy balance, and we have dCA in our material balance, which are two things we really want to solve for to then move on with this problem. Hi everyone, so after we coded everything like I said I would, after we derived everything on the board behind me, I wrote down all of the constants we gathered from right here in the opening problem statement, and I also wrote down some of basically the given equations that we had, the equations we derived. So now that we have everything set in stone, we need to define our function. We're going to define a right-hand side, is what we're going to call it. And right-hand side with, let's see, t and then a vector is how we're calling it. And now we need to unpack this vector It looks not like enough, but we're going to do CA comma T is how we're unpacking this vector. And now we also need to calculate K. So the reason we were calculating K is because K naught times, because it's, as you can see in this equation here, it relies on temperature. NP dot E. I don't think that's right, but it's fine. Negative ER. Negative ER. We're going to divide by T. That doesn't seem right. Yep, no, it looks like it works. So perfect. And now we are going to return our two functions, or our two values. So first, because CA is first, we are going to return CA. And CA is essentially, as we said, QA, or Q over V as our constants, divided by, or multiplied by our CAI, or our inlet, minus CIA, which is coming out of the tank, all subtracted by K times CA. So our in minus our out times what's being used up in the reaction, by multiplied. We are also going to return our energy equation now, which is so very pretty. So, as you can see, we have Q over V times Ti minus T plus HR times K times CA divided by rho times C multiplied by UA times this whole funny thing, but because we have HR, we need to make it negative, or just apply it to what we've named things. So, that did not work. Let's see if this works. All right, that works. So now we need to do solve LVP. Before that, we need a T end, which we are going to call 10, and we're also going to call it 10 minutes, because look at the, I didn't realize this when we were doing time, or deriving the equation, so if you look at everything in here, it's in terms of minutes. Kind of like how I was using meters cubed up there in terms of liters, just because it was a volume unit. I didn't exactly have the right one in my head. So 10 minutes. Now we're going to do resolution equals solve IVP. And what does it require? So function, we're going to do RHS. Then we're going to do the T-span is going to be 0 to T end. That's not a 0. I may have to put brackets around this. I don't remember. There'll be an error, and I will figure it out. And then Y naught. So now this, I know, we have two different Y naughts. We have CA naught and T naught, I believe. If you look up here, we have CA naught and T naught. Perfect. And now our next is going to be our method. So we're going to say method equal, it's read out. That sounds right to me. And then we're going to do dense output equals true, because we want it to be able to be pulled. So now we're going to do that. Let's see, what is the issue? Resolution. Method is not right. Let's see, must be one of these different ones. RADAU. Okay, so it doesn't RADAU, so it means that should work. Perfect. So now we have our values. We can start creating our plots. So we're going to do fig equals make subplots. We also need to do something how we can unpack our values of this vector. So we need to do like, I think we need to do like CA comma T equal res dot sol, and we're going to call this T plot, because this is where we want it, and I think I need to define T plot first. So T plot equals linspace. I always mess up making plots. And then we need to do subplots, and I think we want to do like rows equal 1 and columns equal 2, because we're going to be plotting two different things. Basically, we're going to be plotting the same values, but we have CA and then T. So we want them right next to each other, which is why we have one row, two columns. And I believe I'm messing this up, but that's okay. I can come back and fix it. And then we were going to do, because we want t-plot and x-plot. And I believe this is why we want t-plot, and then we actually want this to be x-plot. Yeah, so I'm going to need to define t-plot as well. Did not need to do that. I don't care. X-plot, which is going to be 0, comma, linspace, and I probably typed it wrong. Linspace 0, 200, comma, and we want t end, because we want 0, 200 points, and then that's from 0 to t end. That may also maybe be the wrong order. Oh, I didn't know that existed. That's kind of cool. So the next part is we need to actually end up doing fig.add and fig adds underscore scatter. Let's see, what does it have here? We're going to do x equals xplot, and we're going to do so we need to do x equals xplot, then t equals tplot, and then we need to then deviate. I think we need to make 2 of these, because we're going to want to add one for, oh crap, we want one for our y-axis, well, one for our temperature, one for our CA. We need to specify, I believe. However, I'm having issues remembering correctly right now, so I am going to double check, and I will be right back. Alright, so it seems I got a little turned around. It wasn't far off, but just enough that I was going to cause an issue. So np, turns out np.linspace is an actual thing. Parameters, we want start, stop, so we need to replace t-end with 200, I believe. This looks right to me. Yeah, start, stop, and how many we actually want. So if start is 0, if stop is 200, we want 200 points. So then we have this. So we have x is going to be tplot. Let's see. And y is going to equal our CA. And then we are going to do row equal 1, comma, call equal 1. And then we're going to do name equals CA. Now we're going to do the exact same thing. So x equals tplot, comma, y equals, let's see, this is temperature, I believe. And then we have row equals 1, because we only have one row, equal 1, call equal 2. That way we have them separated. Then we're going to do name equals t. So hopefully this should work. Alright, perfect. So what you're seeing here is 2 different plots. So this is our CA plot, and this is our concentration plot, and this is our temperature plot. And what you can see is our temperature is dropping. And this is because our cooling is kind of having a little bit too strong of an effect. So when the temperature drops, as you can see up here, our reaction rate, or our K, ends up dropping. When our K drops, because it's exothermic, it basically creates a ramping scale where our temperature starts dropping, meaning our concentration gets more and more, how do you say this? We just have more concentration of A because it's not being reacted with. So you say we kind of have at 305, I believe, see, at 305 cooling, our temperature evens out right around 317 degrees, and our concentration evens out at around 92, 93%. And that's because our cooling is working too well, that it's stemming this reaction and kind of smothering it to death. So I believe that answers the problem of which kind of describing the concentration temperature profiles when the temperature is at 305 at temperature times 0. So thank you for watching.